Hello students, welcome to my class Astrophysics. Today we learn about the conservation of linear momentum and we also learn about some applications of conservation of linear momentum. And already we know in our previous classes what is linear momentum. It is a measurement of motion of a moving object, that is it is a property of a moving object and it is measured by the mass and velocity. It is also a vector quantity. And after that we have also learn about the second law of motion, and in second law of motion we already know the change of the momentum taken place only if there is any external unbalanced force acting on that object. Now today we will learn the conservation of linear momentum. What is the meaning of the conservation of linear momentum? According to this law, the total linear momentum of an isolated system remains constant. Here, one term is the isolated system. The meaning of the isolated system means when there is no external force acting on the system. All the forces are internal one, that means action reactions within the same system. There is no external forces acting on the system. That system is known as isolated system. And according to law of linear momentum conservation, and the total linear momentum of the system remains constant for an isolated system. Alternately, we can say the total linear momentum of the system of several interacting particles is conserved if no external force acts on the system. According to Newton's second law of motion, we know that F, that is the external force or net force, that is equal to dp dt, that is the rate of change of linear momentum if no external force acts. Then F will be 0, this part will be 0, and which indicates dp dt is equal to 0. That means P is a constant. Here P is not the variables. Okay, 0. When dp dt is 0, that means P, the value of the P is a constant. It is a mathematical form of the law of conservation of linear momentum. And if we consider a system of n particles which contains n particles, and that is a isolated systems, that means all the action interactions are taken place within the object or particle in that system, and n number of particles having mass m1, m2, m3 up to mn, and are moving with velocities v1, v2, vn respectively. Therefore, total linear momentum of the systems, that is the sum of all vector sum of all linear momentum, because the linear momentum, it is a vector quantity, and obviously the direction of the linear momentum is always along the direction of the velocity at that moment. So when there are n number of particles in that system, the total linear momentum P will be m1 v1 vector plus m2 v2 vector plus m3 v3 vector plus mn vn vector. That means it is nothing but the vector sum of p1 vector plus p2 vector plus pn vector. That these are the individual linear momentum of each particles of the system. Since there is, if let us suppose if external force be acting on that system, on n particle system, and therefore as a whole we can write F external, that is d dt of p vector, and that can be written in this way, since p is the p1 vector plus p2 vector plus p3 vector and so on plus pn vector. Therefore d dt is the p plus p1 vector plus p2 vector plus pn vector. Again, in the similar way, if we consider there is no external force act on the system, that is F external is 0, in this, from this equation also we can write d dt of p1 vector plus p2 vector plus pn vector equal to 0, and which indicates the sum of p1 vector plus p2 vector plus pn vector is equal to constant, because we know when the differentiation of any quantity is 0, that means that quantity is constant. Differentiation means it is nothing but the rate of change. When the rate of change is 0, that indicates that quantity is constant one. There will be no change with respect to t, that means time. Thus, in absence of any external force, the total linear momentum of the system is conserved or constant, which is law of conservation of linear momentum. And this statement is nothing but the law of conservation of linear momentum. Now we can derive this in another way. Derivations of law of conservation of linear momentum using Newton's third law of motion. And here we will consider two particle system. Let us consider two bodies A and B of masses m1 and m2 forming an isolated system. That means there is no external force acting on the system. Only the interaction between A and B is taken place when they will be in contact. The bodies are moving with velocities u1 and u2 in this figure diagram. And here the direction of the u1 and u2 both are in the same directions. They are moving along the uh, same straight line. And here we consider the numerical value of the u1, it is greater than the numerical value of the u2. And therefore, there is a chance, or there will be a collision between the m1 A and B object, that means mass m1 and m2 after a certain time, because the u1 is greater than the u2 and these two are moving along the same direction. And here collision is taken place. The two bodies collide for the time delta t, and we consider the time of collision or a duration, that is the delta t time, and that should be very small time interval. And after collision, the bodies move with velocities v1 and v2. After that collision, they will moving along the same directions, and we are saying these are v1, the velocity of the A that becomes v1, and velocity of the B becomes v2, and they are moving along the same directions. This type of collision is known as the one-dimensional collision, because before the collision and after the collision, all the collide object, here all the means A object and B object, these are moving along the same direction. The action interaction taken place when they collide each other and for the time interval delta t. And we are observing here there is a change in the momentum of the A and B, and now we have to observe what will be the total change in the momentum, or what will be the total momentum of the system, because there is no here external force acting on the system. Now before collision, what was the total momentum? And that is the m1 u1 for the A, and momentum of the body B, that is m2 u2 before the collision. That means before the collision, or before the interaction between the two objects A and B, the momentum of the system, that is, or that was m1 u1 plus m2 u2. It is before the collision when they are moving and approaching towards each other. And after the collision, momentum of body A, that is the m1 v1, and momentum of the body B, that is the m2 v2. The total momentum of the system, that is m1 v1 plus m2 v2. Therefore, what will be the change in the momentum of body A after collision? And always change is measured by the final minus initial. Change, it is the, we are not indicating change means, that is the difference. Change means final minus initial. Difference means higher value minus lower value. Here we are using a word, the change in the momentum of the body A after collision. That is the final momentum of the A minus initial momentum of the A, and that is m1 v1 minus m2 v2, where v1 is the velocity of the A object or first object after the collision. Similarly, change the momentum of the body B after the collision. The momentum, final momentum or after the collision of the momentum of the body B is the v2 m2 v2 minus m1 m2 u2. During collision, the body A exert a force FAB on the body AB. Now, during the collision, let us here look at the picture. And during the collision, A object exerts some force to the B object, and B object exerts some force on interaction taken place here to the A object. And according to third law, we know these two forces are equal and opposite. That means every action has opposite reaction. We may say that is VFBA, that means force experienced by the B given by the A, and FAB, that is the force experienced by A given by the B. These two are equal and opposite, and we are getting it from the Newton's third law of motion. From the Newton's third law of motion, body B also exert a force FAB on the body A such that FAB is equal to minus FBA. That means these two forces are equal but opposite in direction. Minus sign indicates that is opposite in directions. If delta T be the time for which the collision takes place, then impulse of FAB, impulse means force into time of impact or time of interactions or time of collision. In this case, we are taking that is the delta t. Therefore, what is the impulse? Impulse of FAB collision takes place, then FAB into delta t, and which is nothing but equal to change in the momentum of body A, and we get it from the impulse momentum theorem, that impulse that is equal to the impulse of a force on any object that is equal to the force into time. Measurement of the impulse is the force into time, and that is equal to the change the momentum of that object, and it is also known as the impulse momentum theorem. We already read it, learn it. Now, what is the impulse on object A of this force? That is the m1 v1 minus m2 u2. Similarly, impulse of BA, FBA, that means on the second object, that is the force on the B into time interval. Time interval is the same time duration of the collision, that is same for the A object and B object, and that is change in the momentum. Again, from the impulse momentum theorem, we can write that is the FBA, force into time delta t, is equal to m2 v2 minus m2 u2. That is a change in the momentum of the B object or second object. Now, according to Newton's third law of motion, FAB is equal to minus FBA, and by multiplying both sides this equation by delta t, that FAB into delta t is equal to minus FBA into delta t. Now, from this, and these are nothing but the impulse, and it is also impulse on B, it is impulse on A. Therefore, we already know the FAB into delta t, that is m1 v1 minus m1 u1. Left hand side, that is the m1 v1 minus m1 u1, and right hand side, in right hand side, it is m2 v2 minus m2 u2. That is impulse on the object B. Already we know it by putting the value from equation 4 and 5 in this equation. We get this. And now multiplying by the minus sign, it is a minus, 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 plus, and by calculation we now get m1 v1 plus, it is here m2 v2, which is equal to m1 u1 plus m2 u2, or m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Therefore, total linear momentum before the collision equal to total linear momentum after collision. This proves the law of conservation of linear momentum. That means it is one type of proof of law of conservation of linear momentum with the help of the Newton's third law of motion. Also, from the concept of the impulse and momentum theorem, we can prove it. The total linear momentum equal to the of the system equal to the total minimum linear momentum before and after interactions, after the collisions. Now we are learn about the or know about the some important applications or applications of law of conservation of momentum. Number one, that is the recoil of gun. The gun and bullet both form a system. Before firing the system, before firing the system is at rest, and the linear momentum of the system before firing is 0, and after firing the bullet leaves the gun with a very large velocity in forward directions. So the linear momentum of bullet is very large, as there is no external force acts on the system. So the linear momentum after firing must be 0. It happens only if the gun has the linear momentum that is equal and in backward direction. Then the gun recoils to conserve the linear momentum. That means, first of all, what is the recoiling of the gun? And it is a common experience. And when any bullet is fired from a gun, the gun that moves in backward direction with some velocity, and it is always observed. Now, how can we explain it? We can explain it with the help of the law of conservation of linear momentum. We know when there is no external force acting on the system, the total linear momentum remains constant, and linear momentum, it is also a vector quantity. When the bullet is fired from a gun, the bullet is moving in forward direction with a very high speed with a very high momentum, but initial momentum of the system was 0. Therefore, we can explain it from the law of conservation of linear momentum. total linear momentum after the interaction, that means after the firing of the bullet, that also remains constant. Since linear momentum, it is a vector quantity, and therefore the sum of two vector quantities will be zero when the two are equal and opposite. Therefore, there will be an equal and opposite linear momentum, and that is obtained by the gun. Therefore, gun will recoil in backward directions. We are considering the direction of the bullet motion, that is the positive direction. Then we can say the direction of the gun, that is in the backward, that is negative in directions. We can find out the expression of simple mathematics for the recoil velocity. Recoil velocity is the velocity with which the gun moves backward after firing a bullet. Let us a gun mass M, capital M, fires a bullet of mass small m. Before firing, both gun and bullet are at rest. After firing, the bullet moves with velocity v, small v, but the value is very large. It is denoted by the small v in forward directions. That means we are taking, or we are considering the direction of the bullet as a forward direction. And guns move with a velocity v, capital V here. We are taking capital V, but the velocity will be less in backward directions, as no external force act on the system. So according to principle of conservation of linear momentum, the total momentum of the system before firing equal to total momentum of the system, that is gun plus bullet after firing. Therefore, zero total linear momentum before firing. Both the gun and the bullet they stay together at rest. Therefore, initial momentum is the zero, and after the firing, the momentum will be m v vector plus m capital V vector. That is the vector sum of the two linear momentum of the bullet plus linear momentum of the gun. Now, by calculation, we get m v capital M into capital V equal to minus small m into small v. Therefore, capital V equal to am divided by capital M into V vector. Negative sign shows that V vector and V are in opposite directions. That is, the gun kicks in the backward direction, or the gun recoils with velocity V vectors. Here, the negative sign that indicates the direction of the small v and the capital V both are opposite in directions. That means we can calculate the recoiling velocity with the help of this formula. Since the mass of the gun naturally very larger than the mass of the bullet, therefore from this equation, when mass is large, therefore it will be a fraction. Therefore capital V, the value of the capital V, that will be a fractional value of the small v. That means capital V, that is the velocity or recoil velocity of the gun, that will be very less than of the small v. That is, recoil velocity of the gun is smaller than the forward velocity of bullet, or V mod of V vector, that is inversely proportional to the capital M. Recoil velocity of the gun is inversely proportional to the mass of the gun. So more is the mass of gun, lesser will be recoil velocity, and vice versa. Heavy gun recoils, that means heavy guns recoil smaller than lighter gun. And for that reason, oftenly it is stated that while firing gun must be held tightly with shoulder. While firing gun while firing, gun must be held tightly with shoulder. What are the causes behind this? Now we can explain with the help of this. That means the recoiling velocity, that is inversely proportional to the mass of the gun. When the gun recoils, it may hurt the shoulder. But on holding the gun tightly, body of the shooter and gun behaves as one system. That means the mass of the gun and the mass of the shooter, body mass of the shooter, both are added, because now both are a same object when it is tightly held. Total mass of the system becomes large, and therefore recoil velocity of the gun becomes small. V will be small, and we always want the recoil velocity should be small. Therefore, if you want to fire, then the gun should be tightly hold with the shoulder or with the body of the shooter. Now, another example of this recoiling velocity, machine gun firing bullets. Let us suppose a machine gun fires n bullets in time t. Let us m be the mass and small v be the velocity of each bullet. And there are a large number of bullet automatic machine gun, let us suppose n number of bullets firing in 1 minute, let us suppose. Each momentum of one bullet is the m into v. The total momentum of all bullets in the forward direction, that will be n into m into v. The reaction to this momentum will be in backward direction. In order to hold the gun in position, the applied force should be such that F into T, that is total impulse force into time that, let us say, that is 1 minute, and is the number of bullets in 1 minute or in T minute or T seconds, etc. Then that will be equal to minus n into m into v. That is the force. Now F average force, that is n m v divided by T. That means this amount of force you have to apply to hold the machine gun. If number is more, then you have to apply more amount of forces in the same direction of the machine gun. This is the force applied on the object. Therefore, you have to apply more this amount of plus forces. It is force experienced by the shooter or a holder of the machine gun. Now, another example: explosion of bomb. Let us consider that a bomb is initially at rest. Total linear momentum of the bomb will be 0. Let us the bomb explodes into 4 fragments, mass m1, m2, m4, m3, and their respective history is v1 vector, v2 vector, v3, and v4 vector. Initially, the bomb it is at rest, and after the explosion, here we considering there are 4 fragments. But these 4 fragments, they must be moves in different directions, because the velocities must be in different direction. Total momentum before the explosion of the bomb 0, and obviously after the explosion that must be equal to 0. That means total linear momentum in this case, these, let us suppose m1 mass, first fragment is the mass m1 and velocity v1, for the second velocity v2, for the third velocity v3 and v4. Their linear momentum m1 v1, m2 v2, m3 v3, m4 v4. Since the resultant of all these momentum will be 0, because initial momentum of the bomb that is what at rest, that is 0. The total linear momentum must be 0, and therefore the vector sum of all the linear momentum must be 0. And according to Polygon law, here there are 4 fragments. Therefore, these 4 linear momentums, these can be expressed along the 4 sides of a quadrilateral or polygon in the same order. That means it would be a closed polygon, closed quadrilateral, and for that the velocity is v1, v2, v3, v4. These will be in the different direction. That means when any bomb explodes, the fragments, there are n number of fragments, and they will move in all directions. As no external force acts on the system, then according to law of conservation of momentum, m1 v1 vector plus m2 v2 vector plus m3 v3 vector plus m4 v4 vector is 0. These momentums are responded both in magnitude and directions, represented both in magnitude and directions by sides of a polygon taken in the same order. Hence, the total momentum of bomb after explosion will be 0. When a man jumps out of boat to the shore, the boat slightly moves away from shore. Initially, the total momentum of the system, that is man plus boat, is 0, or maybe some momentum. But when as man jumps from the boat to the shore, he gains momentum in the forward direction. To conserve the momentum, boat also gains equal and opposite momentum, so the boat moves slightly backward direction. And it is our common experience: when we jump from the boat to the shore, then our movement in the forward direction, the boat will slightly move in backward direction. In this way, there are so many examples in our daily life, and you should find out different examples which are related to this law of conservation of linear momentum, and try to explain these phenomena which are happen around you, around us. Then you can again better get understanding about the conservation of linear momentum. Now, equilibrium of concurrent forces. Here mainly we will discuss about the 3 forces. Already we have no equilibrium of 2 forces. The condition for the equilibrium of 2 forces or 2 vectors, when these 2 forces or 2 vectors, they are acting along the same line and opposite in direction. But in case of when there are 3 vectors, in this case we are specifically considered the forces. A body is said to be in equilibrium if the vector sum of all the forces, three forces on the body is 0. Here we consider there may be more number of forces and their resultant will be 0. Then the body will be known as in equilibrium conditions. Concurrent forces means they are acting on the same object at the same time. These type of forces are known as the concurrent forces. Let us here F1, F2 and F3, these are three are concurrent forces here, and the resultant is 0. That means after that the object is at equilibrium conditions. If it is at rest, that will be at rest, or if it is in motion, it will be in motion, uniform motion. That means there will be no change of the velocity, there will be no acceleration. Now let us consider the three concurrent forces F1, F2 and F3 acting at a point on the body. Resultant force F1, F2 give the diagonals of OC. Here the F1 plus F2, that is a resultant of F1 force and F2 forces. We can obtain it from the parallelogram theorem. That means it is the diagonal of the OACB parallelogram, which two sides F1 vector and another side is the F2 vector, this one. And when these three are in equilibrium, therefore the resultant of F1 vector plus F2 vector, that must be equal and opposite to the third vector, that is F3 vectors. That means if the third vector F3 is equal and opposite to the resultant vector F1 and F2 vectors, the F3 vector that will be minus F1 vector plus F2 vector, then the body at point O will be in equilibrium under the action of all three forces. That means F1 vector plus F2 vector plus F3 vector equal to 0. That is, the vector sum of all forces acting at a point on the body is 0. From this, we can also say three concurrent forces will be in equilibrium when the resultant of any two vectors, or here any two forces, is equal and opposite to the third one. That is not only for the F1, F2. If we consider the resultant of F1 vector and F3 vector, that must be equal and opposite to the F2 vector. Similarly, if we consider F3 vector and F2 vector, the resultant of F3 and F2 along this, that must be equal to the F1 vector and opposite in direction. Then the resultant will be 0. And from the triangle law of vector addition, we can also say, we know from the triangle law that three forces F1 vector, F2 vector and F3 vector are in equilibrium when they are represented by three sides of a triangle taken in same order. And for the three vectors, when these are in equilibrium, there is a theorem, that is Lami's theorem. This theorem states that if three forces acting on a particle keeps in equilibrium, this theorem strictly when three forces acting on an object and they are in equilibrium, only for three forces and only when they are equilibrium, we can use the Lamy theorem. Then each force is proportional to the sine of angle between the other two forces. Let us suppose here this figure diagram, F1 vector, F2 vector and F3 vector, these are in equilibrium, and see here alpha is the angle between the F2 and F3, that is opposite to the F1, we can say, rather than F1. This is the each force proportional to the sine of the angle between the other two forces, that is F1, then alpha is the angle between other two forces. When we consider F2 vector, then beta is the angle between the other two forces. And when we consider F3 vector, then gamma is the angle between the other two forces, that is F1 force and F2 force. Now, since these three are in equilibrium, therefore we can represent all the three, F1 vector plus F2 vector and F3 vector, by the three sides of a triangle in the same order, because their resultant is 0 in same order. Now this angle, what is the alpha? Alpha is the angle between the F2 vector and F3 vector. Always the angle between this is the angle. It is not the angle between the two directions. That is, this is the alpha, is the angle between the F2 vector and F3 vector. Similarly, this beta angle between the F3 vector and F1 vector, beta angle. Similarly, gamma is the angle between the F1 vector and F2 vector. Now this angle is, if it is the alpha, this angle is the pi minus alpha. If this angle is the angle between the F3 and F1, be careful about it. This is the angle between the two directions. No, it is not the angle between the F3 and F1. Now it is the beta, then this angle is the, because pi minus beta, because total angle is the pi. Similarly, this angle is the pi minus gamma, because this is the gamma, total angle is the pi, that is the complete angle. Therefore, this angle is the pi minus gamma, and it is the angle between the F1 and F2. Obviously, here also angle between the two directions. Let a particular point O is under the equilibrium of three forces, F1 vector, F2 vector, and F3 vectors. That is, all these are concurrent forces because they are acting at the same point and at the same time. And here we consider the angle between the forces F1 and F2 vector is the gamma. Angle between the forces F2 and F3 is the alpha. Angle between the forces F3 and F1 is beta. That is shown in this figure diagram. Now, forces F1, F2, F3 are represented by the three sides of triangle ABC in same order. Applying law of sines, we know the law of sines from the trigonometry, that is this divided by this opposite sine of opposite angles equal to this side divided by sine of opposite angles equal to this side divided by sine of opposite angles. The value of this side AB, it is the AB represents the vector F1, but the value, numerical value of AB is the F1. Similarly, numerical value of the, that is BC is the F2, and numerical value of the AC, that is the F3. Now from the sine law, applying the law of sines, and that is from the trigonometry, F1 divided by sine of pi minus alpha, this side divided by interior opposite angles of this side, and it is corresponding angle, it is known as, this is the sine of pi minus alpha, which is equal to F2 divided by sine of pi minus beta, F2 divided by opposite angle, this one, sine of pi minus beta, and that is equal to F3 divided by sine of pi minus gamma. This is the F3, and this is value of this side divided by opposite angle sine of pi minus gamma. It is known as the law of sines, and you can get it in trigonometry. And from that, we know the sine of pi minus alpha, that is 180 degree minus alpha, that is sine of alpha. Sine of pi minus beta, that is sine of beta, and sine of pi minus gamma, that is also sine of gamma. And from this, it is now popularly known as the Lami's theorem. Lamy theorem, it is applicable when three forces acting on the concurrent forces, that means acting on the same object at the same time, and after that their resultant is zero, that means these are in equilibrium. And in such a case, equilibrium, that may be static equilibrium, that may be dynamic equilibrium, that means the object may be in continuous uniform motion, equilibrium means, or if it was initially rest, then it will be at rest. Then we can apply this theorem only for the three vectors. Now it is our this module, and now for the next video, you follow the video series.